Hello learners, and welcome to our final lecture about thermodynamics. So new part, new pre-lecture. So that means you want to complete the pre-lecture one-pager to orient your brain. You want to review previous information by reviewing a concept and completing a practice problem related to that concept. And of course, the goal of the lectures is to enhance or add to pre-lecture information so that everything connects. Let's go ahead and get to thinking, folks. We have learned so much about spontaneous changes from our understanding of entropy. Just as soon as we thought the hunt for spontaneous change in Mystic Falls was over, and we predicted and calculated all we could, a bigger supernatural thermodynamic threat has emerged, one causing spontaneous ghosts, as stated in the Mystic Falls Times in this article as we see here. So we're back with the Winchesters to fight this attack, and we need to be able to defeat this threat quickly. So calculating the delta S of the system and the delta S of the surroundings to predict spontaneous change would be tedious. We need something quicker. Something that can be one criterion for spontaneity that we can determine by measuring the system only. A weapon we can wield to measure the spontaneity of a process and the useful energy available from it. A weapon like Gibbs free energy, or simply capital G. And you might be asking, where are we going to get this from? Well, it turns out Bobby knew a guy, and his name was Josiah Willard Gibbs. Gibbs was a visionary theoretical physicist, chemist, and mathematician, and he established chemical thermodynamics as well as major principles of equilibrium and electrochemistry, even though they did stump him a lot when it comes to like Nobel Peace Prizes. Despite his lack of regard, he was able to find a new thermodynamic quantity that is the difference between the system's enthalpy and the product of the absolute temperature multiplied by the system's entropy, in an expression that is G, which is Gibbs free energy, or simply free energy, is equal to H minus Ts. And this is the expression that we are going to use as a weapon to fight this threat. So if G is negative or less than 0, it is going to be a spontaneous process. If G is positive or greater than 0, it's going to be a non-spontaneous process. And if G is equal to 0 itself, then of course the process or the reaction is at equilibrium. And we will continue to learn about this thermodynamic quantity as we go throughout the hunt. Like, we'll learn about Gibbs free energy on its own, then we'll learn about Gibbs in the standard state, we'll learn about the change in Gibbs free energy, and then we'll also learn about the change in the standard state for a reaction. So let's get this hunt organized and use this new free energy weapon. Okay, we'll dive into our new hunt by finding a way to solve for spontaneous change more quickly. This means we have to apply connections from entropy to Gibbs free energy. And we'll get to learn about free energy change and reaction spontaneity, standard free energy changes, free energy and work, temperature and reaction spontaneity, coupling reactions, and then we'll end with free energy, equilibrium, and reaction direction. Very similar to the same kind of concepts we applied with entropy. And as a bonus, we'll join Sam and Dean as they use supernatural thermodynamics to help a family being attacked by a demon. But first, let's visit our Mystic Falls victims who are being attacked by a supernatural thermodynamic ghost. We will learn and apply what we know to save them from this attack. Let's get it, folks.